The universe is supposed to make sense. We have a model. It's called the Lambda-Cold Dark Matter Model, or LCDM for short. It says the universe started with a big bang, it's expanding, and it's made of about 5% normal matter, 27% dark matter, and 68% dark energy. A key part of this model is the cosmological principle. It's the idea that on very large scales, the universe is homogeneous and isotropic. That just means it looks the same everywhere and in every direction. There shouldn't be any special places, and matter should be spread out like a fine, even mist. But there's a problem. A big one. The universe isn't expanding at the rate we think it should be. As of the 2020s, this problem has a name. It's the Hubble tension. Cosmologists like Wendy Friedman at the University of Chicago have spent their careers trying to nail down the expansion rate known as the Hubble constant. The trouble is we have two main ways of measuring it, and they give different answers. One method looks at the very early universe. It uses the cosmic microwave background, the leftover heat from the Big Bang. Satellites like Planck measured this light, and using our standard model of physics, predicted how fast the universe should be expanding today. They get a value of about 67.4 kilometers per second per megaparsec. The other method looks at the local modern universe. Friedman and others use stars like Cepheid variables and type Ia supernovae as standard candles. We know how bright these objects are supposed to be, so by measuring how dim they appear, we can calculate their distance. By measuring their redshift, we can see how fast they are moving away from us. This method gives a different number, around 73 or 74. The two numbers don't agree. Their error bars don't overlap. This isn't a small rounding error. It's a fundamental disagreement at the heart of our understanding of the cosmos. Resolving this Hubble tension is a major goal. Something is wrong. Either our measurements are flawed in some way we don't understand, or our model of the universe is incomplete. The next big discovery is expected to reveal new physics. Maybe dark energy isn't a constant. Maybe there's a new type of particle we haven't found. Or maybe, just maybe, the universe isn't as smooth and uniform as we thought. Maybe the cosmological principle is wrong, and when you start looking at the largest structures ever found, the ones that are far too big to fit into our neat models, you start to wonder if the cracks in our understanding are much larger than we ever knew. These structures are the evidence. They are the anomalies that hint at a bigger, stranger, and more complex reality. Number 25, the Clowes-Campusano LQG is a cosmic anomaly. This structure is over 2 billion light-years across. It was discovered in 1991, which makes it one of the earliest two big structures ever found. It contains 34 quasars. These are not stars, they are the incredibly bright centers of very distant, very young galaxies. A quasar is powered by a supermassive black hole feeding on gas and dust. They are so bright they outshine their entire host galaxy. Finding 34 of them clustered together was a shock. They are spread across a region of space that, according to our models, should be mostly empty. The structure is officially named U-128 because of its average redshift. Its existence was one of the first major challenges to the cosmological principle. At the time of its discovery, the theoretical upper limit for the size of a cosmic structure was thought to be around 1.2 billion light-years. The Clowes-Campusano Large Quasar Group, or CLQ-G, was nearly double that. It was an awkward fact that didn't fit the theory. Roger Clowes and Luis Campusano, the astronomers who found it, used data from the UK Schmidt telescope in Australia. They were systematically surveying the sky for quasars. They weren't looking for a giant structure. They just noticed a statistically significant overdensity of quasars in one particular patch of the sky in the constellation Leo. The quasars had similar redshifts, meaning they were all at roughly the same distance from us, about 9.5 billion light-years away. This meant we are seeing them as they were when the universe was only about 4 billion years old. Finding such a large organized structure so early in the universe's history is a problem. Structures are supposed to grow slowly over time through the gentle pull of gravity. Small things clump together to form bigger things. Galaxies form groups, groups form clusters, clusters form superclusters. This is called hierarchical formation. The sequel G seems too big, too early. There simply hasn't been enough time since the Big Bang for gravity to assemble something so massive. For decades, it was a subject of debate. Some argued it was a statistical fluke, a chance alignment of quasars that weren't really part of a single, coherent structure. But, as our mapping of the universe has improved, the evidence has grown that the LQG is real. You know, it's not a smooth spherical object. It's elongated, maybe filamentary, like a long string of galaxies and quasars tracing a path through the cosmic web. It remains a thorn in the side of standard cosmology. It's a relic from a younger universe that was already more structured than our theories predict. Number 24, the KBC Void is the emptiness we live in. Our Milky Way galaxy is part of the local group, which is on the edge of the Virgo supercluster. But this whole local neighborhood is sitting inside a giant cosmic void. It's called the KBC Void, named after the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who first described it in 2013. This void is the largest one known that contains our own galaxy. It is roughly 2 billion light years in diameter. It's not a perfect vacuum. It has some galaxies, including us, but it has a much lower density of matter than the cosmic average. So we are living in a cosmic underdensity, an emptier than average patch of the universe. This has profound implications. For one, it might help explain part of the Hubble tension. If we live in a giant void, the gravitational pull from matter outside the void would be stronger than the pull from inside it. Matter would be pulled away from the center of the void. This could create a local Hubble bubble where the expansion rate appears faster than the global average. When we measure the expansion using nearby supernovae, we might be measuring this local faster rate. The measurements of the cosmic microwave background, on the other hand, give us the average expansion rate for the entire universe. The KBC Void could account for some of the discrepancy between the two measurements. The evidence for the void comes from looking at the distribution of galaxies around us. When astronomers map out galaxies in 3 dimensions, they see that we are surrounded by a relative lack of them. We are in a sparse region. This idea isn't entirely new. For years, astronomers have noted that the number of galaxies in our cosmic backyard seems a bit low. But the KBC study was the first to quantify it on such a large scale and suggest it was the largest such void yet found. The void's shape is thought to be roughly spherical, with our local group located a few hundred million light years from its center. So we aren't, in the very middle of the emptiness, but we are definitely inside it. This changes our perspective. We often think of ourselves as being in a crowded supercluster. But that supercluster itself is just a small clump of matter inside a much, much larger expanse of nothingness. It's like living on a small island in a vast, empty ocean, and that ocean's currents, the gravitational pulls from the distant shores, might be affecting how we perceive the entire universe. Number 23. The Boss Great Wall is a web of superclusters. Discovered in 2016, this structure is a massive chain of superclusters. It's about 1 billion light years across. Its total mass is estimated to be 10,000 times that of our own Milky Way galaxy. The name OSS comes from the survey that found it, the Baryon Oscillation Spectroscopic Survey. This survey is part of the Sloan Digital Sky Survey. Its goal is to map the universe in 3 dimensions by measuring the positions of millions of galaxies and quasars. A team of astronomers from the Canary Islands Institute of Astrophysics, led by Heidi Lietzen, were analyzing this data. They weren't looking for a single giant object, they were studying the large-scale distribution of galaxies. But in the data, they found a monster. The Boss Great Wall consists of 830 separate galaxies that they could see, but it's organized into 4 massive superclusters. These superclusters are linked together by filaments of galaxies and hot gas. The whole thing forms a single, gravitationally connected system. It's located about 4.5 to 6.5 billion light years away from Earth. This is a significant distance, meaning we are seeing a structure that had already formed when the universe was about half its current age. The structure is so large that it, again, pushes the boundaries of the cosmological principle. While not as outrageously large as the Hercules Corona Borealis Great Wall, it is still among the top 5 or 6 largest structures ever discovered. Its existence provides strong evidence for the cosmic web model of the universe. This model predicts that matter is not distributed randomly. Instead, it forms a vast, interconnected network of filaments, nodes, and voids. The filaments are long strands of galaxies and dark matter. The nodes are the dense regions where filaments intersect, and these are where you find massive galaxy clusters and superclusters. The voids are the huge empty spaces in between. The Boss Great Wall is a spectacular example of this web-like structure. It is a gigantic wall or filament in that web. The debate around it centers on whether it can truly be considered a single bound structure. Gravity acts over very long distances, but over 1 billion light years, the expansion of the universe is a powerful counterforce. It's unclear if the different parts of the Boss Great Wall are truly gravitationally bound to each other, or if they are just a chance alignment that will eventually be pulled apart by cosmic expansion. Regardless, its sheer scale and the density of galaxies within it make it a landmark in our mapping of the cosmos. Number 22. The Giant GRB Ring is an impossible circle. This is not a wall or a filament, it's a ring. A giant ring of gamma-ray bursts, or GRBs, that stretches 5.6 billion light-years across. It was discovered in 2015 by a team of Hungarian and American astronomers led by Lajos Balázs. This structure is so big, it's hard to even comprehend. If you could see it in the night sky, it would be 70 times the diameter of the full moon. It's located about 7 billion light-years away. The ring is made up of 9 gamma-ray bursts. These are the most powerful explosions in the universe, believed to be caused by the collapse of massive, fast-spinning stars into black holes. Because they are so bright, they can be seen from across the universe. They act as markers, like lighthouses, pointing to regions where there is a lot of matter and massive star formation. The 9 GRBs that form this ring all have very similar redshifts, meaning they are at the same distance from us. They appear to be arranged in a near perfect circle on the sky. The probability of this happening by chance is estimated to be 1 in 20,000. That's low enough to suggest it's a real physical structure, but a structure like this makes no sense according to our current models. How could a ring of galaxies 5.6 billion light-years in diameter form? There is no known physical process that can create something like this. And structures are supposed to form from the random, clumpy distribution of matter after the Big Bang. They shouldn't have regular geometric shapes like a circle. The Discovery team proposed a few ideas. One is that we might be looking at the projection of a spherical shell of galaxies onto our 2D view of the sky. This is similar to how the shell of a soap bubble looks like a circle when you look at it. This would mean there is a giant spherical shell of galaxies where massive stars are forming and dying, and we're just seeing the edge of it. This might be related to something called baryon acoustic oscillations. These were sound waves that rippled through the hot, dense early universe. They left behind a faint imprint on the distribution of matter, creating a preference for galaxies to be separated by a certain distance, about 500 million light-years. These giant shells of galaxies could be a manifestation of those ancient sound waves. But the giant GRB ring is 10 times larger than the expected scale of these oscillations. It is another anomaly that defies easy explanation. It's either an unbelievable statistical fluke, or it points to a physical process in the universe that we know absolutely nothing about. Number 21. The Eridanus Supervoid is a cold, empty hole. This isn't a structure made of something, it's a structure made of nothing. It's one of the largest voids ever discovered, a colossal region of space with an almost complete absence of galaxies. It's sometimes called the CMB cold spot. It was first noticed in 2004 in data from the WhatMap satellite, which was mapping the cosmic microwave background CMB. The CMB is the afterglow of the Big Bang, and it's remarkably uniform in temperature, about 2.7 Kelvin. But there are tiny fluctuations, about 1 part in 100,000. These fluctuations correspond to the tiny density variations in the early universe that eventually grew into the structures we see today. The cold spot is a region in the constellation Eridanus that is significantly colder than the average. It's a huge patch of sky, and it's a statistical anomaly. It's too big and too cold to be explained by the standard model of cosmology. For years, its origin was a deep mystery. Was it a flaw in the satellite's instruments? A statistical fluke? Or something much more exotic, like the signature of a parallel universe bumping into our own? In 2007, astronomers pointed radio telescopes at that region of the sky to look for galaxies. They found a huge void. The Eridanus Supervoid is estimated to be between 500 million and 1 billion light-years across. It is located about 3 billion light-years away. The leading explanation for the cold spot is that it's caused by the supervoid. It's a phenomenon called the integrated Sachs-Wolf ISW effect. As photons of light from the CMB travel through the universe, they pass through gravitational fields of large structures. When a photon enters a dense region like a supercluster, it gains energy a blue shift. As it leaves, it loses energy a red shift. In a static universe, these two effects would cancel out. But the universe is expanding, and that expansion is accelerating due to dark energy. By the time the photon leaves the supercluster, the cluster has expanded and its gravitational well is shallower. So the photon doesn't lose as much energy as it gained. The net effect is a slight heating of the CMB light. The opposite happens with a void. A photon loses energy entering the void. By the time it leaves, the void has stretched out and its anti-well is shallower. The photon doesn't regain as much energy. The net effect is a slight cooling, so a giant supervoid in the line of sight could create a cold spot in the CMB. However, the Eridanus Supervoid, as big as it is, doesn't seem to be large or empty enough to explain the entire temperature drop of the cold spot. The mystery isn't completely solved. The void is real, but it might not be the whole story. The cold spot remains one of the most significant anomalies in our data about the early universe, and this giant empty space is at the heart of it. Number 20, the Shapley supercluster is a gravitational giant. This is the largest concentration of galaxies in our local universe. It is a dense, sprawling collection of over 8,000 galaxies. Its total mass is more than 10 million billion times the mass of our Sun. It is located about 650 million light-years away from us in the constellation Centaurus. It was discovered by Harlow Shapley in the 1930s. He was cataloging galaxies and noticed this remarkable concentration, which he called a cloud of galaxies. For a long time, its significance wasn't fully appreciated. It was just one of many clusters. But in the late 1980s, astronomers realized just how important the Shapley supercluster is. They were trying to understand the motion of our own local group of galaxies. Our galaxy group is moving through space at a blistering 600 kilometers per second relative to the cosmic microwave background. What is pulling us? For decades, the prime suspect was a mysterious concentration of mass called the Great Attractor, located about 250 million light-years away. But the Great Attractor alone couldn't account for the full speed of our motion, and then astronomers looked further out. Behind the Great Attractor, in the same direction, lies the Shapley supercluster. It is a much larger and more massive structure. It is now believed that the Shapley supercluster is the dominant source of gravitational pull in our local universe. The Great Attractor is just a stop along the way. We are being pulled towards a region of space that contains both the Great Attractor and the Shapley supercluster. The supercluster is not a single object. It is a collection of dozens of individual galaxy clusters and groups all interacting and merging. At its core is the Shapley 8 cluster, a very rich and dense cluster of galaxies. You know, the whole region is cosmic constructions after where galaxies are, you know, constantly colliding and merging, and huge amounts of hot gas are being stripped away and heated to millions of degrees. Because of its immense mass, the Shapley supercluster is a crucial laboratory for studying cosmology. Its density and size provide a test for our models of structure formation. It also plays a key role in defining the flow of galaxies across hundreds of millions of light years. All the galaxies in our part of the universe, including our own Milky Way, are on a long journey, and the destination sign points directly towards Shapley. Number 19, the South Pole wall bends around us. This is one of the most recent discoveries on this list, identified in 2020. It's a gigantic wall of galaxies that was hidden from view for decades. It's located about 500 million light years away and stretches for at least 1.4 billion light years. It is one of the largest structures ever found in the local universe. Its discovery was made by a team led by Daniel Pomerede at Paris-Saclay University. The reason it was hidden for so long is simple. A large part of it is located behind the plane of our own Milky Way galaxy. This region of the sky is called the Zone of Obscuration. It's filled with gas, dust, and stars from our own galaxy, which block our view of the distant universe behind it. And it's like trying to see a distant mountain range through a thick fog. To find the South Pole wall, the astronomers didn't just look for galaxies directly. They used a new technique. They looked at the peculiar velocities of thousands of galaxies. A galaxy's velocity has two parts: the recession velocity due to the expansion of the universe, and the peculiar velocity, which is its own motion through space caused by the gravitational pull of nearby structures. By mapping these peculiar velocities, you can infer the location of unseen mass. If a lot of galaxies are moving towards a certain point, there must be a huge amount of mass there, even if you can't see it directly. The team's analysis revealed this enormous, curving wall of matter. It is centered on the celestial South Pole. It has a long, sweeping arm that extends north towards our galaxy. The densest part of the wall is in the direction of the South Pole. The discovery of the South Pole wall helps to refine our understanding of the cosmic flows in our local neighborhood. It shows that the gravitational landscape is more complex than we thought. The pull of the Shapley supercluster is still dominant, but the South Pole wall is another major player in the cosmic tug-of-war that dictates our galaxy's motion. It is a reminder that our map of the universe is still incomplete. There are still giant structures, cosmic continents waiting to be discovered right in our own cosmic backyard, hidden just out of sight. Number 18, the Perseus-Pisces supercluster is our neighboring giant. This is one of the two largest known structures in the local universe, along with the Laniakea supercluster, which contains us. The Perseus-Pisces supercluster is a massive filament of galaxies. It stretches for nearly 300 million light years and is located about 250 million light years from Earth. It's one of the most prominent features in the sky when you map out the distribution of nearby galaxies. It was first identified by David Batuski and Jack Burns in 1985. It is a long chain-like structure, not a spherical one. It's a classic example of a galaxy filament. It connects several major galaxy clusters, including the Perseus cluster Abell 426 and the Pisces cluster. The Perseus cluster is one of the most massive objects in the nearby universe. It contains thousands of galaxies and is a powerful source of X-rays from the hot gas that fills the space between the galaxies. The supercluster is so large that it spans more than 40 degrees of the winter sky. What makes the Perseus-Pisces supercluster particularly interesting is its relationship to our own cosmic neighborhood. It borders a large void, the Taurus void. On one side of us is the dense Perseus-Pisces supercluster. On the other side is this large empty space. This arrangement of a dense filament and a large void has a significant gravitational effect on the galaxies around it, including our own local group. We are essentially on the edge of the Laniakea supercluster, being pulled towards the Great Attractor, but the Perseus-Pisces supercluster and the Taurus Void also influence our motion. It's part of the complex gravitational web that defines our place in the cosmos. Studying the structure of the Perseus-Pisces filament helps astronomers understand how these large-scale structures form and evolve. They believe it formed from the collapse of a long, thin sheet of matter in the early universe. As gravity pulled the matter together, it fragmented into the clusters and groups we see today, all strung along the original filament. It's a fossil record of the very early density fluctuations that shaped the universe. Number 17, the dipole repeller is a push, not a pull. For a long time, we thought our galaxy's motion was all about being pulled. We are pulled by the Virgo cluster, the Great Attractor, and the Shapley supercluster. But in 2017, a team of astronomers led by Yehuda Hoffman discovered that we are also being pushed. They found a huge, previously unknown void in the opposite direction of the Shapley supercluster. They named it the dipole repeller. This void is incredibly empty. It has a very low density of galaxies. Just as a concentration of mass pulls things towards it, a lack of mass effectively pushes things away. It's not a real repulsive force. It's just that the gravitational pull from the matter on the other side of us is much stronger than the pull from the direction of the void. So we are squeezed out of the void and pulled towards the denser regions. The dipole repeller is a major part of the explanation for our galaxy's motion. The edipole in our motion refers to the fact that we are moving in one specific direction relative to the cosmic microwave background. The Puel from the dipolar crit. The discovery was made using the same technique of mapping peculiar velocities. The team analyzed a huge catalog of galaxy motions called Cosmic Flows 3. This catalog contains detailed information on the distances and velocities of over 18,000 galaxies. By mapping how these galaxies are moving, they could create a 3D map of the underlying mass distribution, including the voids. The map revealed this giant empty region right behind our galaxy. This discovery fundamentally changed our picture of the local cosmic flow. It's not just a simple one-way trip toward Shapley. It's a more complex dynamic of being pushed from behind and pulled from the front. The existence of the dipole repeller reinforces the importance of voids in shaping the structure of the universe. They are not just passive, empty spaces. They are active components of the cosmic web, exerting a powerful influence on the evolution of galaxies and superclusters. Number 16, the Great Attractor, remains a mystery. This is perhaps the most famous cosmic mystery on this list, but it's still not fully understood. In the 1970s, astronomers discovered that our Milky Way and its neighboring galaxies are all streaming towards a specific point in the sky in the direction of the constellations Hydra and Centaurus. The speed is enormous, about 600 km/s. There had to be something there with immense gravity, a Great Attractor pulling everything in. The problem was, this region is located directly behind the zone of obscuration, the dusty plane of our own galaxy. It was impossible to see what was there with optical telescopes. For years, the Great Attractor was a gravitational anomaly without a clear source. In the 1980s and 90s, astronomers started to pierce the veil using X-ray and radio telescopes, which can see through the dust. They found the Norma cluster Abell 3627, a massive galaxy cluster located about 220 million light years away, right in the heart of the Great Attractor region. The Norma cluster is very massive, perhaps 10 times more massive than the Coma cluster. So it seems to be the core of the Great Attractor. However, the mass of the Norma cluster alone is not enough to explain the entire gravitational pull we observe. It only accounts for a fraction of the motion. This led to the discovery of the much larger Shapley supercluster, which lies beyond the Great Attractor and provides the rest of the pull. So, the Great Attractor is not a single object. It's a diffuse region of overdensity, a gravitational center of a much larger structure, the Laniakea supercluster. The Norma cluster is its core, but the pull comes from a whole collection of galaxy clusters and filaments spread across hundreds of millions of light years. Even today, mapping this region is difficult. You know, the zone of obscuration still makes it hard to get a complete census of all the galaxies there. The Great Attractor is less of a single thing, and more of a gravitational focal point. It's the place where the filaments of the cosmic web in our part of the universe converge. It's the bottom of the gravitational valley that we are currently rolling into. Number 15, the Coma Wall, is a filament in our backyard. This structure is a galaxy filament. It is part of the Coma supercluster and is one of the more prominent walls in the nearby universe. It was first mapped in detail by Margaret Geller and John Huchra in 1989 as part of their pioneering CFA2 redshift survey. Their survey produced the famous Stickman figure, a slice of the universe showing that galaxies are not spread out evenly. They are arranged in long filaments and vast empty voids. The Coma Wall was one of the first of these large-scale structures to be clearly identified. The wall is about 500 million light-years long, 300 million light-years wide, but only about 15 million light-years thick. And it's a relatively thin sheet of galaxies. It is located about 300 million light-years from Earth. The most prominent feature within the wall is the Coma cluster Abell 1656, an extremely rich and dense cluster containing over 1,000 identified galaxies. Another major cluster in the wall is the Leo cluster Abell 1367. The Coma Wall forms one side of the Coma supercluster. It is a textbook example of the kind of structure predicted by the cosmic web theory. It's not as enormous as some of the great walls found at greater distances, but its relative proximity means we can study it in great detail. We can observe the individual galaxies within it, study how they are interacting, and see how the filamentary structure influences their evolution. For example, galaxies within the dense clusters of the wall are more likely to be older, redder elliptical galaxies, while galaxies in the less dense parts of the filament are more likely to be star-forming spiral galaxies. This suggests that the environment of the wall is accelerating the aging process of galaxies, stripping them of their gas and shutting down star formation. The Coma Wall is a crucial piece of the puzzle in understanding our local cosmic geography. It is one of the boundaries of the Great Void in front of the Coma supercluster, often called the Boots Void. It helps define the large-scale structure of our cosmic neighborhood. Number 14, Laniakea, is the supercluster we call home. For a long time we thought we were part of the Virgo supercluster. In 2014, that picture changed. A team led by Brent Tully at the University of Hawaii published a new way of defining superclusters. Instead of just looking at the distribution of galaxies, they looked at their motions. They mapped the peculiar velocities of 8,000 galaxies in our local universe. This allowed them to define the boundaries of superclusters based on gravitational flows. A supercluster is a region of space where all the galaxies are flowing towards a common center of gravity. Everything inside the boundary is flowing inwards. Everything outside is flowing away. Using this definition, they mapped out a new supercluster. They named it Laniakea, a Hawaiian word meaning immense heaven. Laniakea is huge. It is 520 million light-years across and contains about 100,000 galaxies, including our own Milky Way. Its total mass is about 100 million billion times that of the Sun. The Virgo supercluster is now understood to be just a small lobe, an appendage of the much larger Laniakea. The gravitational center of Laniakea is the Great Attractor region. All the galaxies within Laniakea, including us, are on a path towards this point. The boundary of Laniakea is the line where the gravitational influence of the Great Attractor is balanced by the influence of neighboring structures, like the Perseus-Pisces supercluster. If a galaxy is just inside the line, it will fall towards the Great Attractor. If it's just outside, it will flow away towards Perseus-Pisces. This definition provides a more physically meaningful way to describe these large structures. Laniakea is not a gravitationally bound object in the traditional sense. The expansion of the universe is so strong on these scales that Laniakea will likely never collapse into a single object. The different parts of it are moving away from each other, even as they all flow towards a common center. It's more like a watershed or a river basin on Earth. All the water in a basin flows towards a single river, but the basin itself is not a single object. Laniakea is our home gravitational basin in the universe. For number 13, the Pisces-Cetus supercluster complex is a galactic wall. This is a galaxy filament, but on a much larger scale. It's a supercluster complex, a chain of superclusters. It is estimated to be about 1 billion light-years long and 150 million light-years wide. It is one of the largest structures identified in the nearby universe. It was first studied by Brent Tully in 1987. The complex contains our own Laniakea supercluster as one of its main lobes. It also includes the Perseus-Pisces supercluster, the Pisces-Cetus supercluster, and the Sculptor supercluster. It is a massive interconnected network of galaxies. This structure is so large that it is pushing the limits of what we consider a local structure. It connects our cosmic neighborhood to the larger cosmic web. It's a cosmic highway of galaxies stretching across a huge volume of space. The Pisces-Cetus supercluster complex is estimated to contain about 60 major galaxy clusters and have a total mass of about 10 raised to the power of 18 solar masses. That's 1,000 times more massive than Laniakea. This makes it one of the most massive objects in the local universe. Like other filaments, it is thought to have formed from the collapse of a large sheet-like overdensity in the early universe. Its existence provides strong support for the hierarchical model of structure formation, where small structures merge over time to form progressively larger ones. We see this process in action within the complex, with clusters and superclusters interacting and merging. The study of this complex is important for understanding the overall architecture of the universe. It shows how superclusters themselves are not isolated islands, but are connected into even larger structures. It helps us trace the filaments of the cosmic web and understand how they channel matter and influence the evolution of galaxies over cosmic time. Number 12, the huge LQG is too big for our theories. The Huge Large Quasar Group, or Huge LQG, is another one of the cosmic giants that shouldn't exist. It was discovered in 2013 by a team led by Roger Clowes from the University of Central Lancashire. It is a collection of 73 quasars. It stretches about 4 billion light-years at its widest point. At the time of its discovery, it was the largest known structure in the universe. It's located about 9 billion light-years away. Like the Clowes-Campusano LQG, its existence is a direct challenge to the cosmological principle. The principle suggests that on scales larger than about 1.2 billion light-years, the universe should be homogeneous. The huge LQG is more than 3 times larger than this theoretical limit. The quasars in the group were found using data from the Sloan Digital Sky Survey. They all have similar redshifts, indicating they are at a similar distance and likely part of the same structure. The structure is not spherical, it is very elongated and filamentary. The sheer size of the huge LQG is the main problem. There just hasn't been enough time since the Big Bang for a single structure this large to form through gravity. It would require gravity to act much faster or over larger distances than our current theories allow. The discovery sparked a lot of debate in the astronomical community. Some studies have questioned whether it is a real, coherent structure. They argue that the algorithm used to identify the group might be picking up random alignments of quasars. A study in 2016 suggested that the statistical evidence for the huge LQG being a real structure is not as strong as initially thought. They argued it might be a chance projection of several smaller structures. However, the original discovery team stands by their findings. They point out that the probability of such a large grouping of quasars happening by chance is extremely low. The debate is ongoing. The huge LQG, along with other similar structures, sits on the razor's edge of our understanding. If it is real, it means our standard model of cosmology is missing something fundamental about how the universe is put together on the very largest scales. It's number 11. The Sloan Great Wall was once the record holder. The King. Discovered in a long time. This was the King. Discovered in 2003 from the data of the Sloan Digital Sky Survey, the Sloan Great Wall was the largest known structure in the universe for nearly a decade. It is a gigantic galaxy filament. It measures 1.37 billion light-years in length and is located approximately 1 billion light-years from Earth. It was discovered by J. Richard Gott III and Mario Jurek and their colleagues at Princeton University. The wall was found by analyzing the 3D map of galaxies from the Sloan survey. In the data, this enormous, continuous structure stood out clearly. It is a vast, twisting ribbon of galaxies containing several superclusters. The most massive of these is the SCL 126 supercluster. The total mass of the wall is hard to estimate, but it is certainly one of the most massive structures known. Like the other Great Walls, it is not a gravitationally bound system. The different parts of it are not all orbiting a common center. The expansion of the universe is pulling it apart. It is a transient structure, a feature of the cosmic web at a particular moment in time. However, its existence still posed a challenge to some cosmological models at the time. While it is just barely within the theoretical size limit of the cosmological principle around 1.2 billion light-years, it is right at the edge. Finding such a large structure suggested that the distribution of matter in the universe might be lumpier than expected. The Sloan Great Wall is a spectacular example of the Great Wall type of structure. These are the largest sheet-like or filamentary structures in the cosmic web. They form the boundaries of the great cosmic voids. The discovery of the Sloan Great Wall, and later the even larger structures, has forced cosmologists to refine their models and simulations of structure formation. They need to be able to reproduce these giants in their computer simulations to be confident that they understand how the universe works. Number 10, the giant arc bends across the sky. This is another recent and baffling discovery announced in 2021 by Alexia Lopez, a PhD student at the University of Central Lancashire. The giant arc is a colossal structure that stretches for 3.3 billion light-years. It is located 9.2 billion light-years away, so we are seeing it when the universe was less than 5 billion years old. What makes it so strange is its shape. It's a nearly symmetrical arc of galaxies, a giant crescent on the sky. It appears as a smooth curve of galaxies, quasars, and gas. It is so large that it would span about 1/15 of the radius of the observable universe. The giant arc was not found by looking for galaxies directly. It was discovered by looking at the light from distant quasars. As light from a quasar travels towards us, it passes through gas clouds and galaxies. These clouds absorb some of the light at specific wavelengths, leaving a fingerprint in the quasar's spectrum. Lopez and her colleagues analyzed the spectra of about 40,000 quasars from the Sloan Digital Sky Survey. They were looking for the absorption lines of magnesium ions, which trace the location of intervening galaxies and gas clouds. They found a huge continuous pattern of absorption systems forming a giant arc. The statistical significance of this arc is very high, meaning it is extremely unlikely to be a chance alignment. Its existence is a major problem for cosmology. It is almost 3 times larger than the theoretical size limit imposed by the cosmological principle, and its smooth, curved shape is not something that is easily explained by the random gravitational collapse of matter. It is located in the same part of the sky as another giant structure, the huge LQG. They are at similar distances from us. This has led to speculation that they might be part of an even larger system. The giant arc is so new that the astronomical community is still trying to figure out what to make of it. It's a profound anomaly. It suggests that the processes that shape the universe on the largest scales might be different from what we think, and that the universe might be less random and more structured than our theories predict. Number 9, the U111 Large Quasar Group. This is another massive quasar group, similar to the huge LQG and the cyclic G. It was discovered by Roger Clowes' team in 2011, just before they found the huge LQG. It's about 2.5 billion light-years across. It contains 38 quasars and is located about 8.8 billion light-years away. At the time of its discovery, it was one of the largest structures known. It is designated U111 because of its average redshift. Like the other LQGs, it challenges the cosmological principle. It is about twice the theoretical size limit for a cosmic structure. It was also found using data from the Sloan Digital Sky Survey. The discovery of U1.11 and then the even larger huge LQG shortly after was what really brought the issue of these 2 big structures to the forefront of cosmological debate. It showed that the Clowes-Campusano LQG, discovered 2 decades earlier, was not a one-off fluke. These giant quasar groups seem to be a real feature of the universe, at least at the epoch when the universe was a few billion years old. The existence of these structures suggests that the early universe was much lumpier than predicted by the standard model. The matter density fluctuations that came out of the Big Bang might have been larger on very large scales than we thought. This could have seeded the formation of these giant structures much earlier than expected. This would have significant implications for our understanding of inflation, the period of rapid expansion right after the Big Bang that is believed to have created these initial density fluctuations. The large quasar groups are fossils from that early time, and their enormous size is a clue that our story of the universe's beginnings might need a rewrite. Number 8. The Hercules Northern Crown Great Wall. This is the smaller of the 2 great walls in this region of the sky, but it's still gigantic. It's a galaxy filament that is part of the Hercules superclusters. It is about 600 million light-years long. It was one of the large-scale structures mapped by the early redshift surveys in the 1980s. It lies about 500 million light-years away. The Hercules superclusters themselves are 2 large superclusters that are close to each other. This Great Wall connects them. It's a major feature of the cosmic web in our medium-distance neighborhood. It forms part of the boundary of the Boots Void, one of the largest known voids. The structure is a classic example of how superclusters are not isolated entities. They are nodes in a larger network connected by these immense filaments or walls of galaxies. Studying the Hercules Northern Crown Great Wall helps us understand the dynamics of this region of the universe. The galaxies within it are all moving along the filament, eventually falling into the dense superclusters at its ends. It's a river of galaxies flowing through the cosmic web. The wall is also a good place to study how environment affects galaxy evolution. By comparing galaxies in the dense clusters to those in the more sparse regions of the filament, astronomers can see how processes like galaxy mergers and gas stripping are driven by the local density of matter. Number 7, the Boots. Void is the Great Nothing. Also known as the Great Void, this is one of the most famous and largest cosmic voids. It was discovered in 1981 by Robert Kirshner, Augustus Oehmler, Jr., Paul Schechter, and Stephen Schechtman as part of a redshift survey of galaxies. They were surveying 3 small patches of the sky. In 2 of them, they found a normal distribution of galaxies. In the third one, in the direction of the constellation Boots, they found almost nothing. They kept expanding their survey, expecting to find the edge of the void, but it just kept going. The Boots Void is a huge, roughly spherical region of space. It is nearly 330 million light-years in diameter. Its volume is about 236,000 cubic megaparsecs. To put that in perspective, if our Milky Way galaxy were at the center of the Boots Void, we wouldn't have known other galaxies existed until the 1960s. The void is not completely empty. In 1987, the astronomers found a few galaxies inside it. By 1997, a total of 60 galaxies had been identified in the void. They seem to be arranged in a kind of tube or filament structure running through the middle of the void. The existence of such a large void was initially a surprise, but it fits well within the cosmic web model. These voids are the natural consequence of gravity pulling matter into filaments and clusters. The regions in between get evacuated, forming voids. The Boots Void is just a particularly large example. Its study is important for understanding the dark energy that is causing the expansion of the universe to accelerate. The evolution and shape of voids are very sensitive to the properties of dark energy. By studying the distribution and shapes of voids, like the one in Boots, cosmologists can place constraints on their models of dark energy. The void is also a kind of time capsule. The few galaxies that live inside it are in a very low density environment. They have evolved in isolation without the frequent mergers and interactions that galaxies in dense clusters experience. They might be pristine examples of how galaxies form and evolve without outside interference. Number 6, the CFA2 Great Wall was a paradigm shift. This was the structure that changed everything, discovered in 1989 by Margaret Geller and John Huchra from the Harvard-Smithsonian Center for Astrophysics CFA. The CFA2 Great Wall was the first truly enormous cosmic structure to be identified. It is a galaxy filament that is 500 million light-years long, 300 million light-years wide, and only 15 million light-years thick. It is located about 200 million light-years from Earth. The discovery was a complete shock. At the time, most astronomers assumed that on large scales, galaxies were more or less randomly distributed, like raisins in a cake. The CFA2 redshift survey, which Geller and Huchra were conducting, was designed to map the positions of galaxies in 3D. When they plotted their data, they didn't see a random distribution. They saw the stickman, with galaxies arranged in this huge, thin wall bordering a giant void. The discovery of the CFA2 Great Wall was the first strong evidence for the cosmic web. It showed that the universe has a structure on scales much larger than anyone had anticipated. It was a paradigm shift in our understanding of cosmology. It moved the field away from studying individual galaxies and clusters to studying the large-scale structure of the universe as a whole. The wall is a complex structure containing several major galaxy clusters, including the Coma cluster and the Hercules cluster. For a long time, its exact size was debated because it extends beyond the boundaries of the original survey. Subsequent surveys have shown that it is part of a much larger network of filaments. The CFA2 Great Wall is a landmark in the history of astronomy. It was the first Great Wall to be found, and it opened our eyes to the true scale and architecture of the cosmos. Number 5, the Corona Borealis supercluster is a cosmic megacity. This is one of the most prominent superclusters in the northern sky. It is located about 1 billion light-years away in the constellation Corona Borealis. It is an extremely rich and dense supercluster. It is notable for its high concentration of massive galaxy clusters. The supercluster contains about 8 major clusters of galaxies, all packed into a relatively small volume of space. The most famous of these is Abell 2065, a very dense and centrally concentrated cluster. The entire supercluster is estimated to be about 330 million light-years long and 130 million light-years wide. The Corona Borealis supercluster is a perfect example of a node in the cosmic web. It's a region where multiple filaments of galaxies are intersecting and merging. The high density of matter in this region makes it a site of intense gravitational activity, where galaxies are constantly colliding, clusters are merging, and huge amounts of gas are being heated to X-ray emitting temperatures. This supercluster is a crucial testing ground for models of structure formation. By studying the properties of the clusters within it and how they are interacting, astronomers can learn about the process of hierarchical merging, where small structures combine to form larger ones. The supercluster's distance means we are seeing it as it was about 1 billion years ago, giving us a snapshot of how these massive structures were assembling at that time. It's a glimpse into the ongoing construction of the cosmic web. Number 4, the Horologium Reticulum supercluster is a southern giant. This is the second largest supercluster in the local universe after the Shapley supercluster. It is located in the southern sky in the constellations of Horologium and Reticulum. It is a massive structure stretching for about 550 million light-years. It is centered at a distance of about 700 million light-years, but its full extent reaches up to 1.2 billion light-years. And it was discovered in the 1980s through optical surveys of southern galaxies. The supercluster is composed of about 34 major galaxy clusters. Its core contains 2 massive clusters, Abell 3266 and Abell 3128. It is a very dense and massive structure, comparable in richness to the Shapley supercluster. The Horologium Reticulum supercluster is another major player in the gravitational landscape of the local universe. While Shapley is the dominant attractor for our region, the Horologium Reticulum supercluster is another significant concentration of mass. It, helps to shape the flow of galaxies over a vast volume of space. Its study is important for building a complete picture of the mass distribution in our cosmic neighborhood. Like other superclusters, it is a laboratory for studying galaxy evolution in high-density environments. The intense gravitational fields and frequent interactions within the supercluster have a profound effect on the galaxies that live there, transforming them from star-forming spirals into passive elliptical galaxies. Number 3, the Saraswati supercluster is a distant wall of galaxies. Discovered in 2017 by a team of Indian astronomers, Saraswati is one of the most distant and massive superclusters ever found. It is located 4 billion light-years away in the direction of the constellation Pisces. It is a huge wall-like structure stretching for at least 650 million light-years. It is a network of at least 43 massive galaxy clusters and groups. The total mass of Saraswati is estimated to be about 20 million billion times the mass of the Sun. This makes it one of the most massive structures in the universe. Its name comes from the Hindu goddess of knowledge, music, art, wisdom, and nature, and also from a lost mythical river mentioned in ancient Indian texts. The discovery of Saraswati is significant because of its distance. We are seeing it as it was when the universe was about 10 billion years old. Finding such a massive and well-developed supercluster so early in the universe's history is a challenge for our models of structure formation. Structures are supposed to grow slowly over time. Saraswati seems to have formed too quickly. Its existence suggests that the early universe might have had the right conditions to form these giants much faster than previously thought. This might require adjustments to our understanding of dark matter and dark energy, the main drivers of structure formation. Saraswati is a crucial data point in our quest to understand how the cosmic web was assembled. It's a snapshot of a cosmic metropolis under construction in the distant past. Number 2, the Einosto supercluster is a nearby behemoth. This is another recently identified supercluster named in honor of the Estonian astronomer John Einosto, one of the pioneers of large-scale structure research. Discovered in 2018, it is located about 3 billion light-years away. It is one of the richest and most massive superclusters found in the Sloan Digital Sky Survey data. The Ionosto supercluster is estimated to be about 360 million light-years in diameter. Its total mass is about 26 million billion solar masses, making it even more massive than Saraswati. It consists of several hundred galaxy clusters and groups. What makes this supercluster particularly interesting is its richness and density. It is one of the best examples of a node in the cosmic web found at this distance. It is a place where the universe is at its most dense and active. The discovery of such massive superclusters in large volume surveys like the Sloan survey is crucial for testing cosmological models. The number and mass of the most massive superclusters are very sensitive predictions of these models. Every time a new most massive supercluster is found, it provides a new data point to check if our theories are on the right track. The Ionosto supercluster, with its extreme mass, pushes these models to their limits. It confirms that the universe is capable of building these truly enormous structures, and it provides a clear target for future studies to understand the physics of galaxy and cluster formation in the most extreme environments. Number 1. The Hercules Corona Borealis Great Wall is a structure so big it shouldn't exist. This is the current champion, the biggest thing we have ever found in the universe. It is so big that its existence is a profound, fundamental problem for our entire understanding of cosmology. It is a gargantuan filament of galaxies, a great wall. Its size is almost unbelievable. It is estimated to be 10 billion light-years long. That is more than 10% of the diameter of the entire observable universe. It was discovered in 2013 by a team of astronomers led by Istvan Horvath, John Hakila, and Zsolt Bagoli. They weren't looking at galaxies, they were mapping the distribution of gamma-ray bursts GRBs in the sky. GRBs are the most luminous explosions in the universe, and they can be seen from extreme distances. They are thought to be associated with the deaths of massive stars, so their location should trace the location of galaxies and large-scale structures. The team noticed a significant overdensity of GRBs in a patch of the sky in the direction of the constellations Hercules and Corona Borealis. These GRBs had similar redshifts, putting them at a distance of about 10 billion light-years. This means we are seeing this structure as it was when the universe was only 3.8 billion years old. The existence of the Hercules Corona Borealis Great Wall completely shatters the cosmological principle. The principle, which is a cornerstone of the standard cosmological model, states that the universe should be homogeneous on scales larger than about 1.2 billion light-years. This structure is nearly an order of magnitude larger than that limit. There is no known mechanism in our current model of the universe that can assemble a single coherent structure that is 10 billion light-years across. There simply has not been enough time since the Big Bang for gravity to act on such a scale. The discovery is controversial. Some scientists argue that the clustering of GRBs might be a statistical fluke, or that GRBs are not a reliable tracer of the underlying matter distribution. They question whether it is a single, gravitationally related structure. However, the statistical significance of the GRB clustering is high. If the Hercules Corona Borealis Great Wall is real, it means that our standard model of cosmology is not just incomplete, but fundamentally wrong on the largest scales. It could mean that the initial density fluctuations from the Big Bang were much larger than we thought. It could point to new physics, to forces or processes that we have not yet imagined. This structure is the ultimate anomaly. It is a question mark written across the entire sky, challenging everything we think we know about the universe.